I'm Naofumi Homma, session chair. We have 3 talks in this session. The first speaker is Nikolai Muras, please. And the paper entitled Automated Generation of Fault-Resistant Circuits. Okay, Nikolai, so stage is yours.
Slides are shown, perfect. Yeah, many thanks for the nice introduction, and yeah, also welcome from my side to this talk titled Automated Generation of Fault-Resistant Circuits. As you might imagine, as the session is already titled, we talk about faults, of course. So we consider a cryptographic hardware device which implements some kind of crypto and executes it by using a secret key, which is usually stored on the device. And I think the problem here is already clear. We can inject faults into our device in order that it does not behave as extended. For example, by means of clock glitching, or by EMFI, or by focused laser beams, or many more. So in this case, we can, for example, get a faulty output back, which allows us to get information about the secret key, for example, by means of differential fault analysis or CIFAR. So a well-known countermeasure, or maybe most of the families of countermeasures against fault injection attacks based on introducing some form of redundancy in order to detect or correct faults. For example, we can see a little toy cipher circuit here, where we basically have an encryption function, for example, the AES round function, which is just implemented twice in order to detect with a comparison module if there was a fault injected or not. In this case, a flag is raised if the fault is so-called effective, so meaning that a fault that is injected also propagates to the output, so it's visible at the output as a fault. However, the problem is that this error flag indicates whether a fault was ineffective or effective, and therefore can be used or can be exploited in order to run CIFAR on it, so this does not prevent against CIFAR. So we consider in this talk error correction, which can be, for example, done by means of majority voting. So in this case, we have to implement our encryption function 3 times in order to use majority voting to correct faults. In this case, none of the faults should affect the primary output. So basically, all faults are rendered ineffective, which prevents against CIFAR. So basically, when we now have our circuit, the natural question arises how we can prove its security. So how we can guarantee that our circuit is really secure. And from this, we have some fault injection adversary models, and we, in this thesis, took a very conservative model derived from another work, which basically allows an adversary to inject arbitrary faults at arbitrary locations, and in total, F faults simultaneously, so in the same clock cycle. And when we now take this adversary model, maybe one step back, to model this fault, we can just replace a faulted cell by another cell, which basically implements the functionality of our fault. So based on this, we can use some kind of tools here, for example, Verfi or Fiverr, which basically check if a circuit is fault secure, so if all the faults injected are indeed ineffective. We can do this, for example, on the circuit we showed before, so on our majority voting circuit. And here we already see that things become complicated because when we, for example, inject a fault in the encryption function, everything is fine, but if we just inject a single fault in the register, it gets propagated to all the encryption functions and can therefore not be corrected anymore. So this would, for example, be insecure in our model, but what we can do to correct it is just remove the register and run the whole encryption 3 times. So in this case, the encryption module changes to somehow, for example, a full AES or something like that. So in a round-based way, for example, which then runs 10 clock cycles. But the problem here is, if it runs 10 clock cycles, we can inject F faults in every of these clock cycles, so 10 times F, which is then very hard to correct with a majority voting module. So in this case, we cannot do this with 3 encryption modules, but many, many more. So this is some kind of impractical for what we want to do. And we consider another method to correct faults based on error correcting codes. I just want to give a brief background on it. So basically, we consider a code which just maps a message to a so-called code word. Let's see here. For example, in this case, we have a 2-bit message and map it to a 5-bit code word. This we can do for all messages we have with 2 bits. So in this case, 1, 2, and 3. This is just a code I found out before, so Doesn't matter how we found this exactly, this will be discussed later. The point is that this code has some properties, and the most important one here is the so-called minimum distance. This means that every code word of this code has a Hamming distance to all other code words with a minimum of, in this case, for example, 3. So we can just XOR them, compute the Hamming weight, and see that they all have 3 different bits. This holds for all the code words jointly. So why is this important? Because when we have a minimum distance of 3, we can use this code to correct a 1-bit fault. And how is this done? When we consider, for example, faulty code words, so just the red bit here, fault is injected, which switches here from 0 to 1. So you can see this code word is not in the code, but we can correct it just by searching for the code word which is the nearest to it depending on the distance, which is this. When we now XOR them, we get the error vector, and we can now just apply the error vector to this faulty code word to get back to the original code word, which is then corrected. In hardware, such a procedure can look like this, which is based on so-called syndrome decoding. So in hardware, you can implement this syndrome decoder based on these 3 functions. The P function basically just maps the message to the redundancy bits, so not to the full code word, but just to the last 3 bits in this case. And then based on this, a syndrome is decoded, which is then used to correct it. We will discuss later. So based on this error correcting codes, we can construct a countermeasure against faults, which is called impeccable circuits 2 and presented in the paper with the same name. So basically the idea here is to apply this error correcting codes in order to secure, for example, a whole cipher against faults. This is done by 3 different steps. First of all, our whole computation is splitted into a regular part and a redundant part. So we operate on a message state and a redundant state. Then we have to limit the fault propagation with respect to the so-called independence property, which we discuss on the next slide. But just keep in mind here that we have to limit our fault propagation in some case. And then it's just applying the code to correct faulty code words here. So when we now consider our unprotected circuit, it can usually model like this as a Mealy machine, where we have a combinational logic, so all the combinational cells together with a multiplexer, which we now refer to as R, so this whole block is called R, and the single register stage. Basically, you can model every circuit like this. And what impeccable circuits 2 does, it transforms this in a circuit that looks like this. So what we can see here, first of all, we have basically this correction logic in the first part here, where we can see the syndrome decoder module and an F function. And this F function is basically P, but just applied on the whole state. So it maps the whole state to its redundant representation. Then we have the function from before, this R function, combinational logic plus multiplexer. And we have also its redundant part called R prime, which is basically a composition of 3 functions. The first one just maps the message to the parity to the message, sorry. Then the whole R function is computed on the message as usual, and afterwards it's mapped back to the redundant representation. You also see this red boxes here, and this red boxes indicates that all the modules inside of it must follow this independence property. So getting this independence property is quite hard. It's very expensive because the circuit gets very large. So in impeccable circuits 2, they also showed an optimization, which is based on splitting the round function into multiple subfunctions. So basically, you can take the R function and split it into multiple functions, which are corrected by multiple correction points. Then it becomes a little easier to achieve the independence property, but you need also more correction points. So, independence property, what does it mean? So, I want to show you a quick example about it. So basically, following the independence property means that a fault injected in one of the gates is not allowed to propagate to more than 1 output of this whole module. So, for example, if we inject a fault here in R0, then it's got splitted on the wire and propagates to 2 outputs, so this does not follow the independence property, and we have to modify the circuit according to it. For example, we can just duplicate R0, and in this way, we don't have the same property here. So in this case, it follows the independence property, and fault to our circuit just only affect one of the output wires. So the question remaining now is how we can do that. So how we can do this transformation from an unprotected circuit to a protected one. And we know, for example, from the side channel domain that such tools already exist to protect the circuit against side channel analysis. For example, we know about AGEMA, or we know about Compress, which is presented at this year's CHES, so you can join the talk if you are interested in. But how about faults? Can we do the same to automatically protect our circuit with impeccable circuits too? This is the question we want to answer in this talk, and of course, the answer is yes. Otherwise, I would not be here. And the follow-up question is then, what happens if we have a mask circuit? So if we combine these tools for side channel analysis and for faults. So basically, we wrote a tool which does this transformation, which is called AGEFA. And this is the basic workflow this tool does. Unfortunately, it's too much for this talk, so we can only discuss some properties, and I want to answer 3 questions here. The first one is, how can we find an error-correcting code? How can we achieve the independence property? And what happens if we consider masked circuits as an input of our tool? First of all, with respect to the code, we allow the user to choose a message size and the maximum number of faults to correct. And AGEFA can automatically find a code which does this based on a greedy approach, which constructs the so-called lexicographic code. I don't want to go into detail about that, but just give some points which are important. First of all, such a code exists for all possible K and F. This is proven. This code is provably linear, systematic, and injective, which is important here that it works. And usually N, so the code word size, is minimal. Not always, but close to minimal, which is here important to get an efficient output result, so get an efficient circuit which is protected. This can be done by AGEFA. However, if you have your own code which you want to use, you can also provide it, so we don't have to get this code automatically. However, getting such a code with minimal n is probably not always the best choice for this. We just consider one code with a 4-bit message and an 8-bit code word. And we consider this p function, which maps the message to its parity, so 4-bit message mapping to 4-bit parity. And you can see the 4 coordinate functions of it. Here it's not important how they are calculated, it's only important what inputs they got, because now we have a problem. When we consider r prime, this p function is the last component of r prime. So based on this function, we have to achieve our independence property back through this whole down layer, which is red. And this can be very expensive. So what we want to do is, we want to minimize the number of inputs which this function has, because this makes it easier to achieve the independence property. And here we have 9 different inputs. So question is, can we do it better? And yes, we can. If we consider a larger code, we probably have less inputs here. So in this case, only 8, which is some kind of a trade-off, because of course the code gets larger. So yeah, harder to get here. But maybe the independence property is worth it. So this is an optimization we can do with AGEFA. So you can just let AGEFA search a code which is larger but has less inputs per coordinate function. So when we have the code, we can just get all the functions, for example, a syndrome decoder, which you can just get by creating a lookup table and then generating, for example, the A and F of it. So here for the P function and for the syndrome decoder modules, so mapping message to parity and parity to message. This is the most important part. And yeah, this can be easily done. The only problem is that these functions are incomplete and therefore contain don't care values, meaning that we can optimize it for most efficient functions. This can be done, for example, by Quine-McCluskey if you want to get the most optimal results from AGEFA. However, this takes some time, so we also have the operations to ignore don't care values, so just set them to some fixed value and get the Boolean function out of it. So when we have all different layers, we have to achieve the independence property, as I said. So I want to give a quick example for the r prime I showed before, because usually this would be implemented like that. So we have coordinate functions for the r function, which here has 4 bits, and also for the p function, which also has 4 bits. You can see here this does not follow the independence property because, for example, faulting r0, then the output propagates to multiple of the p functions, and you have multiple outputs faulty. So what we have to do is we have to duplicate a lot of these functions to get something which looks like this. And this is, of course, expensive because many modules we need multiple times, but it's the only way here to follow the independence property. So 2 questions answered out of 3. So the last one, what happens if our circuit is already masked, so protected against side channel analysis? In this case, of course, our masked circuit processes a shared state, so which is separated into multiple shares. So every message of our state is also separated into multiple shares. And we have to handle them in a way that they are not combined back accidentally. So what we can do is relatively easy. We can just do all this error correction in a share-wise way. So if we have our correction point and we have multiple shares, for example, in this case 2, we can just use 2 correction points here. The only thing we have to consider is that none 2 shares are given to the same correction point. So for example, if you have a message with multiple bits, don't combine multiple shares in this message. How can we do that? First of all, the trivial way, setting k to 1, then only 1 bit is given to your correction state, and you cannot combine something because it's only 1 bit, so not multiple bits. If you still want to use more than 1 bit per message, which can be sometimes efficient or sometimes not, then you have to provide AGEFA with an additional report where you show just which signal belongs to which share domain, which then basically says, okay, you're not allowed to combine 2 values from the same share domain, so AGEFA automatically reorganizes all of your values in a way that only values from the same share domain go to the same correction point. So this is basically all we did. What we then did is some case studies, so just try if our tool works. For this, we consider a lot of publicly available cipher cores from GitHub, basically from the original Git of AGEMA, where already some ciphers are taken. In this case study, we consider the following ciphers, so AES, Skinny, Craft, Present, LED, and Midori in round-based or serialized implementations. We check different settings for AGEFA. First of all, different message sizes from k equals 1 to k equals 8, just to see which of them are most efficient or not. We allow different maximum distances. So in this case study, we consider 3 and 5, just to ensure that they are still, that we still can check them at the end, otherwise the circuit gets too large. And we consider with and without optimizations, meaning that we optimize the code, so larger codes or non-larger codes, depending on the coordinate functions. And we check with and without decomposition of our input value. So as I said, on the slide with impeccable circuits 2, we can consider our round function as multiple subfunctions. This we also tried. In total, these were 150 different case studies here, which we all measured and evaluated and checked how large they are. I just want to discuss one of them, which was Craft. The reason for that is that Craft was also investigated in the original paper of impeccable circuits 2. So here we can compare our results. Basically, we can see the area and delay overhead with respect to the unprotected Craft core. So what we can see is, first of all, cipher level majority voting, which is not secure in our model, but of course more efficient. So if this fulfills your needs, you can still try that. However, we also have the impeccable circuits implementation with a minimum distance of 3 and 5, and the results of AGEFA. In this case, we can see here that the area overhead as well as the latency is slightly higher for AGEFA, which is, I think explainable because of course you can try more optimizations when you do a handmade design instead of an automated one. So they are slightly more efficient, but we are still comparable here. And what you can also see is that impeccable circuits 2 adds no overhead with respect to the latency, so you don't need more clock cycles to execute. So we also considered a masked case study. So for this, we again took the Craft core, give it to AGEMA, and afterwards we had a masked design, which is provably secure. This we gave to AGEFA to also add fault protection. And this final output we then verified with Verfi and with ProLead, just to show if it's secure against faults and against side channel analysis. So the natural question is, how's the overhead? And the unfortunate answer is high. So when we apply AGEMA, we get a first overhead in the area with a factor of 10. And after applying AGEFA, we get the next overhead with a factor of 10. So in total, a factor of 100, which is super large. But this is more the case study just to show that it is possible to do that, and not a recommendation to apply that, of course. For the latency, it's not that bad, but still we have an overhead in latency, of course. Okay, to sum this up, we introduced AGEFA, an automated framework to generate fault-tolerant hardware. where we can apply impeccable circuits too to protect against faults, and introduced some optimization techniques to improve the area and the critical path delay as much as we can in an automated setting. And we can also apply this to a masked circuit without violating the security proofs of the masking. However, and now the downside begins, we cannot guarantee security against combined adversaries, just against fault injection and side channel attacks separately, but not combined. We have a substantial area overhead, of course, due to the error correction, and at the moment we have no support for detection, which would probably make it smaller in another adversary model. And unfortunately, we can also only correct very precise faults. So only if some very few bit number of bits is faulted, we can correct it. If you, for example, use EMFI and fault multiple bits, we cannot correct them anymore. So this tool is available on GitHub, on the same link as Agema is available, so feel free to try it out, and I would be happy to have some feedback if it works or not. Thank you very much. I'm now very happy to answer your questions.
Thanks for your talk. Okay, so any comments and questions? So if you have any questions, please come to the microphone directly and ask him.
For talk.
Many thanks.
You said you used Quine-McCluskey algorithm for optimization. Did you consider heuristic variants like espresso to make it faster?
Not so far, to be honest. I mean, this is in the end just one optimization out of many. So probably you can improve that by using other more sophisticated algorithms, but we did not try it out. It was just more showing that it works in somehow. Another point is that we only considered small message sizes, which makes the functions also very small. So for us, Quine-McCluskey was at least enough if we have some time for it. So it was no need in this sense to optimize it further. But of course, if you want to try larger codes with larger message sizes, it could be worth it.
Makes sense. Thank you.
Any questions, comments? So could you show me the slide 14? It's a result.
Yeah.
Okay, so what's the difference of the delay and the latency? So delay increased a little bit, but in total latency is almost the same.
I'm sorry, I can explain it. With delay, I mean the critical path delay, and with latency, I mean the number of clock cycles needed to execute this function. So basically, when I say the delay is increased, I mean that the critical path gets longer, which is quite natural due to the insertion of this correction point, which of course increases the latency, but it does not increase any more register stages, for example.
Oh, okay.
I added this because this is a common problem for the side channel stuff, because there Agema, of course, inserts some register stages.
Okay, thanks. Any other comments and questions? I have one more question about optimizations. So this is a result of after the optimization, right?
Yeah.
So
I mean, in this table, I just showed my best results. So as I explained, I made a lot of case studies. So also for Craft, we have message sizes 1 to 8, so 8 case studies. We have maximum distances. So here I showed them all. And then with and without optimization, so 16 results, and with and without decomposition, so 32 results, I think. And therefore, I picked the best one.
Okay. So could you comment on how much the effect of the optimizations? How much improve the performance?
This fully depends on the cipher you give into. So I cannot say that one of the optimizations just took 10% of the area or something like that. This fully depends on what you get in. So sometimes it has a significant impact, up to, I would say, 30%, for example. Sometimes it has no impact at all. Sometimes the optimizations make it worse. So I can give some recommendations about how to choose this parameter, but this fully depends on what you give in.
Okay, thank you. Yes, please.
In the same table, can you explain the distance 3 for the 3 different cases just one more time? I'm getting confused as to what is the difference between the different...
Why we have the different minimum distances?
You had minimum distance for the cipher with majority voting, with impeccable circuits 2, and with AEFA. So what are the main 3 differences between those 3 classes?
Okay. I mean, first of all, the results which are here named Impeccable Circuits 2 are the designs they created with the Impeccable Circuits 2 paper. So these are basically handmade designs. So some engineer sits down, had the craft implementation, and manually adds this countermeasure. So this is made by hand. So here you have a lot more chance to improve stuff. The AGEFA results are the one I generated with my tool. So I just gave the craft circuit in without any optimizations and take the output without any handmade optimizations. This answers your question? Great.
Okay. Any other question, comments? So let's thank the speaker again. Okay, so let's move to the second talk. Okay, second speaker is Ilara Topraxa. Okay, so the paper entitled STATI, Protecting Against Fault Attacks Using Stable Threshold Implementations. Okay, Ilara, please.
Thank you. So this is our work, STATI, Protecting Against Fault Attacks Using Stable Threshold Implementations. And this is co-authored by Simon Doge and Artemi Ovchinnikov. Yeah, so this is a countermeasure against physical attacks, side channel and fault attacks, but this is already covered by many talks today, so I will skip at least this slide. But I will spend a tiny bit of time in the fault attacks, but only the last part. So I want to categorize the fault attacks into two, basically. The ones that exploit wrong ciphertext and the one that exploits data-dependent fault propagation. So the most common countermeasures, we have redundancy and is combination with masking. So these are effective against the attacks that are exploiting wrong ciphertext, because in a simple way that we check the output correctness, and if the output is wrong, then we basically detect the fault. But the data-dependent fault propagation, meaning the fault is sometimes not propagated to the output, then there's no way that we can detect by checking the output correctness. So we need some new methods to protect against this kind of faults. So let's see what is data-dependent fault propagation on a simple example. And this is a truth table of AND gate. We have two inputs and one output. And now we inject a fault to Y, and it's of the form bit flip. And this is the new values of Y. So now we change one of the inputs, and obviously we expect some changes in the output as well. And this is the new updated output. And now what we see here is the output is only changed for half of the input combinations. And when we go back to X, we see that the output is changed when only the X is 1. So we see that the fault is ineffective if the input X is 0, and the fault is effective if the input X is 1. So then the attacker is gonna know that, yeah, X is 1 if the output is wrong. So we can talk about two ways to protect against this kind of faults, and different from the first presentation, I will be focusing on error detection only. So the first way is we can error check all the critical values. For example, in this AND gate, we can error check both inputs, and here we're gonna see that there's a fault injected to Y, and then we're gonna abort, so yeah, we are secure against the fault. And the second way is we can ensure the fault propagation, so we can make sure that all the injected faults propagate to the output. And in this work, we go with the second choice, and we propose STATI, which extends threshold implementations using linear encoding. And with this method, we benefit from only a single error check at the end of the circuit. And before going into details of the countermeasure, first let's see what we are protecting against and what are our security claims. First, we assume well-known deprobing model, and to capture the physical effects of glitches in the hardware, we extended to glitch-extended robust probing model. And to capture the capabilities of a faulting adversary, we assume K-gate register faulting model. And in this model, the adversary is capable of choosing K gates or registers in the circuit, a total of K, and then they're able to change the outputs of these gates. And the change can be of the form reset, set, or flip. And in this work, we specifically assume first-order probing and first-order gate register faulting security, which means a probing adversary can observe only one wire in the whole circuit, or they can change the output of a single gate or single register. So what we expect as the security, the probed intermediate value is independent of any secret variable, and this is coming from probing model. And next, we expect the circuit to be correct and private, meaning the circuit is gonna either abort or it's gonna output a correct ciphertext, and the abort signal is not gonna be dependent on the secret input. So now we know what we are protecting against, what are our security claims, and these are the basics of the countermeasure. First, we make use of Boolean masking, where the secret input is split into a number of shares, and the sum of those shares gives back the secret input. And specifically, we make use of threshold implementations. And threshold implementations, we split the computation into a number of coordinate functions, and each coordinate function computes a single output bit. And for the encoding, we use binary linear codes. And we specifically assume a systematic code where a code word consists of the data itself and the parity bits of the data. And throughout this work, we will be calling a correct encoding a code word in the given linear code. And we are using two matrices in this work. P is gonna be the matrix that we compute the parity bits of the given data, and H is gonna be the matrix that we use for parity check. For example, if we multiply H with a given code word, then it's gonna give a 0 if the input is a valid code word. And in this work, we share the input first and then we encode it. For example, if we use duplication, then we're gonna duplicate all the shares of the given input. Okay, so now we know everything about the countermeasure, like the basics and our security model, and let's see the properties of the countermeasure itself. And first, we have correctness, non-completeness, and uniformity. And these three properties are coming from TI, actually. Correctness means if we give an input to the function, then we get the sharing of the desired output. And non-completeness means each of the coordinate functions operate on data that is independent of the secret input. And uniformity means if the input is uniform, meaning for a fixed input, we have a uniform sharing, and the output is also uniform. But we know that these three properties are not enough to protect against especially ineffective false, and it has been also shown in some research papers, so we need some more properties. First, what we propose is fault non-completeness. This means no gate is shared between two coordinate functions. This solves some of the problems we have. So now we know that any single gate injected to a coordinate function affects only a single output bit, and this fault is independent of the secret input because of the non-completeness. This is fine, but what happens if we inject a fault to the input, or this faulty output is input of another function? So we need some more properties for that. And for this, we propose stability, which ensures that for any incorrect input code word of a shared and encoded register-to-register function, the output code word is also incorrect. And then we have the following theorem. The serial composition of correct, non-complete, uniform, fault non-complete, and stable shared functions is secure against a single probing adversary and a single gate register faulting adversary in a non-combined attack scenario. So the probing security is okay because it's proven in TI actually. And for the single gate register faulting adversary, first we're gonna check the gate false. So this is a given function, and assume that this function has all the properties mentioned in the theorem. We inject a fault to one of the coordinate functions, and this is propagated to the single output bit. We can detect it if this is the last function of the circuit. But if this function is connected to another function, then what happens? So stability says that if the input is faulty, then output is gonna be faulty as well. So now we can detect this as well. So now we know that if a circuit has these properties, then it's secure against single gate register faulting adversary. So now we know what is stability, but we still don't know how we can secure the circuits. And first, let's start with XOR and AND gates, because they are the most basic operations in the cryptographic primitives. But they are finding of two single output functions, meaning they map two different input combinations to the same output. So meaning if the second input combination is faulty, then it's gonna be mapped to a correct output, which is not stable. And I'm gonna show it in some basic examples. First, we have the XOR gate. And now we duplicate this XOR gate. So A prime is equal to A, and B prime is equal to B. And now the input code word is correct, output code word is correct because they're just duplicated. And now we inject a fault to A and B, and it's of the form of bit flip. Now the input code word is not correct anymore because A plus 1 is not equal to A prime, and B plus 1 is not equal to B prime. But the output is still A plus B, which is equal to duplicated part. So the output is still correct, which means this is not stable. So we can say that if there's a fault injected to A, either A or A prime, at the same time there's a fault injected to B or B prime, we know that XOR gate is not stable and the fault is not going to be propagated to the output. And let's see what happens with the AND gate. So first we have the input A, and the second input is assumed to be 0, and we know that output is 0. Again, we duplicate it. A prime is equal to A. And input code word is correct, output code word is correct. And now we inject a fault to A, and A becomes A plus 1. And now the input code word is not correct anymore because this is not equal to A prime. But the output is still 0 because the second input was 0. So the output code word is still correct, which means if there's a fault injected to A or B, and the other input is 0, then the fault is not going to be propagated to the output. Okay, so we know that they are not stable, but how we can find the stable encodings of them? And these are the two basic examples of stable XOR and AND gates. What we do here is we add an error term to the output if the previous case is satisfied in the previous slide. So meaning for the XOR gate, we add an error term if there's a fault injected to A at the same time B. And for the AND gate, we add an error term if there's a fault injected to A and B is 0, or the other way around, if there's a fault injected to B and A is 0. And these are verified to be stable. And now we know how we can get the stable encodings of XOR and AND gates, but this doesn't say anything about how we can secure the whole circuit because there are a lot of XOR and AND gates in a circuit. So we are proposing two general methodologies for an arbitrary function to be stable. The first one is using error detection. So we have a function which is correct, non-complete, and uniform encoded sharing of f. Then we have a global check value, which is r, and it's set to 0 initially, which means there is no fault injected to the circuit. And what we do is, when we compute the function, we also update r by using the h matrix. And h was used to do error check of the input. So here, when we do the multiplication of the input code word with the h matrix, the output is going to be 0 if there's no fault injected to input, and the output is going to be 1 if there's a fault injected to input. If there's a fault injected to input, then r is going to be updated to 1, and at the end of the circuit, we can just detect it. And if r is not 0, then we are going to abort. And the second methodology is interpolation. So we have a function, and it takes x and maps it to y, and we have a shared and encoded version of it. And now what we can do is we list all the correct input code words, and we list all the correct output code words. And next, we list all the incorrect code words of f, and we choose an invalid, so incorrect output code word. And what we do next is we map all the correct input code words to the correct output code words, and we map all the incorrect input code words to a randomly chosen incorrect output code word. So now we know that this list is finite, which means by using interpolation, we can find such a function which is shared, encoded, and stable by using interpolation. So we've seen how we can derive stable encodings of arbitrary functions, and let's see what we can do about t+1 threshold implementations, where t is the degree of the function. So first, let's focus on the linear functions. We have an invertible function L, and P is the matrix that we compute the parity bits. And the following construction is stable. And it's also correct, and how do we know it? We can translate it to this thing. So if there's no fault injected, P of x is equal to x prime, so they cancel each other. And what is left is the parity bits of the output. So this shows that this construction is correct. And we know it's stable because L is invertible, and this construction is permutation, which means if there's a fault injected to the input, it should be mapped to an incorrect output. And it's easy to extend it to shared domain because of linear properties. We can just apply it to share by share. So this is also easy. And for nonlinear functions, let's assume that we have a permutation f, and it's uniform and non-complete sharing. Yeah, we have that sharing. And we know that this is also permutation. And the following construction is stable and correct encoding of that function. And how do we know it? And it's same with the previous slide. P of x is equal to x prime. So if there's no fault injected to the input, they cancel each other. And the following is the parity bits of the output. So we know it's correct. And we also know that it's stable because I can find the inverse of this construction, which means if there's a fault injected to input, it's going to be mapped to an incorrect output because I can go back from the output. So we have seen what we can do with T+1 threshold implementations, and let's see what we can do with stable two-shared threshold permutations. So we can't really find non-complete uniform solutions that has the same number of inputs and output bits. And what we can do is we can base on the work of reconsolidating first-order masking schemes. And in this work, they propose uniform and non-complete sharings of 4-bit quadratic functions. And they operate on 2 shares and also 2 cycles. And now we just need to make sure that both cycles are stable. So this solution is given in that paper. And what we can do here is we can take all the XOR and AND gates, and we can replace them with the stable ones that I showed in the earlier slides. And this construction is again stable, and it's also verified with the software. And now, until now, we talked about some small functions like S-boxes, but now let's see what we can do when we take the whole state of a cipher. Assume that this is the state of the cipher, 4 by 4, and this is a common construction, for example, like in AES. What we do here is we take a row of the state, and we take the parity bits of each element in the row, and now we take the summation of them. And now this is the parity bits of the given row. In this case, we know the shift rows is free because we are not changing anything in the construction of a row. And mixed columns can be directly applied to the parity column. So this is also quite cheap. And what we can do about nonlinear layers is this is going to be the same strategy with T+1 threshold implementations. So what we're going to do is we're going to compute the function on each of the state elements. And for the parity part, we're going to compute the function and take the parity bits of it. And then we're going to add the existing parity bits just to satisfy the correctness of it. And this was the theory part of the countermeasure. And in the practical part, we applied it to Ketchak. So we protected Ketchak F 1600 bits using StatEI, and we implemented it with 2 and 4 shares. And we verified the stability of the implementation using VerMFI, and this is an open source tool for fault verification. And what we saw was there's no overhead in time compared to unencoded TI, and which is a plus. And for the area overhead, we did some comparisons with our implementations, and which is applied on single Ketchak S-box, a Ketchak S-box applied to the whole Ketchak state, and the complete Ketchak implementation. And the first is the comparison table of single Ketchak S-box. In this table, we compare our implementation with the implementation from Young Diamond. And in the countermeasure from Young Diamond, they're using Toffoli gates as the most basic operations in the circuit. So what we see here is we have a huge gain for the cycles, but when we check the area, yeah, even though there's 10 cycles, the area is much better than our implementation. And for the Ketchak S-box applied to whole state encoding, the most interesting part here is we have a huge gain in the state size, but we don't have a gain in the area, because in the previous slide we have seen that the statewide encoding is especially useful in linear layers, but not in nonlinear layers, and this is a table for S-box. So we don't really see a huge gain in the area. And this is a table for complete CHES, the full CHES implementation. And we compare it. First, we have the unprotected implementations, and we know that they're not stable. And we simply duplicate those unstable implementations with 4 and 2 shares. And not surprisingly, the simple duplication of 4 shared implementation is stable. So this is okay. But for the 2 shared implementation, this is not stable, so we need some more properties to make it stable. So we apply StatTI. And what is nice about it here is we don't really have much overhead with respect to area, and we have a stable encoding by using StatTI. So to conclude the presentation, in this work we propose stability, and then we formally define the security of stable threshold implementation against a single gate register faulting adversary. We propose stable encodings for XOR and AND gates. And we also propose general methodologies to transform any arbitrary unstable encoding to a stable one by using error detection or interpolation. And we also propose methodologies for stable T+1 and 2 shared threshold implementations, and also proposed a statewide encoding. And then we evaluated our countermeasure using CHES implementation. Thank you for listening.
Thank you very much. Okay, so any comments and questions? So your countermeasures are against the ineffective fault attacks, right?
Yeah.
So also your countermeasure also prevent some DFA type fault attacks?
Yeah, so we use encoding, and yeah, which protects against DFA kind of attacks, because then we can detect if the output is wrong or not. And DFA works by a wrong output.
Okay, thanks. So any question or comments? Okay, I have one more question.
Yeah.
So can you extend your countermeasure to the higher orders attackers? I mean, multiple point probing or?
Yeah, in this work, we left it as a future work, actually, because it's not this easy. For example, if the faults are injected in different cycles, what we can do is we can introduce error check after each cycle. And if it's in the same cycle, it's even more trickier, because the injected fault can be canceled by the injected other fault. Yeah, so this needs more study.
Okay, thanks. Okay, no questions? Okay, so let's thank the speaker again. Okay, so let's move to the third speakers. Okay, the third talk in this session, the speaker is Jen Yuan Liu. The paper entitled Fault Detective, Explainable to a Fault from the Design Layout to the Software. Okay, maybe soon. Okay. Not this one. Not this. No, this is the first talk.
Yeah, that's right.
Yeah. Okay, please.
Okay, hi everybody, welcome to this session. My name is Charlotte. Thank you for being here. This is the last presentation for the day. Today I introduce you Fault Detective, explainable to a fault from the design layout to software. So I'm going to talk about what is fault root causing and why do we care about it, and then some related work. Also, I will introduce a very important concept. It's called dynamic state transition graph. We'll be able to use this graph to visualize fault patterns. And at the end, I'll introduce fault detective and a demonstration. So what is fault root causing? We have a fault being injected in the hardware, and the fault continues to propagate until we see fault effects in the software. To explain this, so explaining the low-level hardware effects from high-level software observations is fault root causing. And why do we care about it? So current software observations are either we see a faulty output, or there are no effects, or your CPU is stopped. But we wanted to know more than that for root cause analysis. And we aim to just to know more than the intermediate output effects. Therefore, because we wanted to know when and where the initial fault happened, and how does the fault propagating from hardware to software? What's the impact on hardware and software? And then we will have improved designs and achieve cost saving. So the current researches include simulation-based research. It is based on a fault model and include a bunch of different attacks. But with this, it assumes the specific location of faults. And it can explain low-level details, but it depends on the accuracy of the fault model, which can be not practical. And we also have empirical research. It can observe the real-world effects of faults, but it has limited visibility into low-level hardware details. And it cannot explain the effects of faults in the hardware, in the high-level software. So this is where Fault Detective comes in. It will be able to bridge the gap between the simulation and empirical research. It will also help you to locate where the fault root cause is and show its propagation. Therefore, we'll be able to visualize the fault behavior in graphs. Before going into Fault Detective, I wanted to introduce two very important concepts here. It's called architecture and microarchitecture states. For example, we have an application. It has the highest high abstraction level of the finite state machine representation. Includes input and outputs and initial to final state transitions. And a little bit deeper, we have the software level, which includes the assembly code. At the very bottom, we have our hardware, includes gates, registers, and muxes, and the ISA sits in between here. Okay, so now we have a design that all the registers are here now presented with a scan chain. This is at the bit level in the hardware, and all these registers are connected through the scan chain. In order to form an architecture state representation, we will take all the programmable visible bits from the scan chain. So all these register bits, basically you can directly control from the C code or software, any software level controllable registers, we consider them programmer visible bits. And we gather all these bits in a hierarchical order to form in the word level, and at the end, we will form one state, and this is what we call the architecture state. And the architecture state will represent all the programmer visible bits in the hardware. And also, same thing, for microarchitecture, we will use all the visible and non-visible bits, namely all the bits in the design, all the register bits in the design, and we'll also gather them together in a hierarchical order to form them in the word level, module level, and at the end, we will have one state that will represent all the bits in the design, which is we call microarchitecture state. So now, what's next? Because now you can see there are two hierarchical tree structure here to form the hierarchical and microarchitecture state from the leaf to the root. Therefore, I know for sure any changes at the leaf node will result a change at the root node. And this is extremely helpful for the fault root cause analysis. For example, I have some registers that is faulty at the very bit leaf level, and I know now where one will be faulty because of this tree structure, and eventually architecture state top A will be affected by the fault. Same thing for microarchitecture, word 1 and word 2 will be faulted, and they will cause module 1 to get faulted. At the end, microarchitecture state will be faulted. So by looking at this tree structure, we're able to backtrack from the root node to identify which leaf or intermediate node is faulty, and will be extremely helpful for the fault root cause analysis. Instead of to represent the architecture and microarchitecture state with millions of bits, because all these are formed by the low-level bits, we will implement a hash tree. Therefore, every single node here will represent by a unique hash value, and by comparing and looking at the hash value, we will know that where exactly the fault happened and how it's being impacting all the way in the design. Yeah, so now we form a architecture state digest, and also we form a microarchitecture state digest. And remember, all of these digests are represented by unique hash value. And this hash value is representing at that specific clock cycle, what are the status of all these registers. By having this, any changes from the leaf or intermediate node will cause a different hash value in the root digest. And this will be helpful for the root cause analysis. Not only we now can trace which register, which bit, which module is faulty from the root digest, we will also be able to visualize it in graph. So now I introduce dynamic state transition graph here. So for architecture state level, we will plot architecture dynamic state transition graph. Basically, we will plot it per instruction based on the PC jumps. We're able to plot all these digests in an actual graph to present. For microarchitecture, we also have MDSTG, and it will plot it per clock cycle. So by looking at the graphs here, we will have a dynamic state transition of what happened in the system. Therefore, we'll be able to track the system behavior in graphs. So I'm going to give you a small example on how these graphs help in fault root cause analysis. I have a very simple implementation here. It's a switch case between two cases. The big idea is that if the input is 0, the output will be 0. And if the input is 1, the output is 1. And this is the ADSTG and MDSTG. Remember, all these bubbles, the node here, these represent the architecture state, which was formed by the hash tree node from all the programmer visible bits. The same thing for microarchitecture, these represents the states. And then this combines all the register bits together to form with the hash tree. And we also have transition time here to emphasize the dynamic state transition. And for ADSCG, again, plotted with an instruction transition, and then for MDSCG, we have per cycle transition. So you can see here that these two graphs from this implementation gives like 32 clock cycles of a round trip and just continuing between these two states. And all of these bubble states here, A0 all the way to A4 and M0 all the way to M5, these are we call same states. Same states which can achieved in accordance with the programmer's intent. And all the combinations of all possible same states, we call it the same machine. So now DSTG is able to present you the system of the same machine here with this application. And let's see what happened after fault is injected. So I have a fault that's injected at clock cycle 29, and it changes register R2, toggled the bit 03 to 13. This register R2 is a special register, and because of this bit changes, it will disable further instruction fetch and stop the processor. And let's see what the graph tells us. So now we can see that at clock cycle 29, there's some path that is being generated, and then new states is being generated in triangles until we hit A6 and AM7, and now we enter this self-looping stage. Therefore, it sort of tells you that, okay, the CPU is no longer continuing, and then it's stuck in one stage. And we call all these new generated triangle states weird states, which are the behavior that occurs when the same state enter an otherwise unreachable state. And the collection of all possible weird states, we call it the weird machine. So now, by having the same machine and the weird machine together in this dynamic state transition graph, we will have architecture same state, microarchitecture same state, architecture weird state, and microarchitecture weird state. By having DSTG in both architecture and microarchitecture, we're able to visualize the same machine in black, the weird machine in red, and also with this graph, we're able to help us in the fault analysis because it shows where and when the initial fault happened and how is this propagating. And not only that, we're able to summarize 4 patterns in this paper. First, we have wormhole, where the weird machine was generated and it just started to do whatever it wants and started to continue. We also have spinner, which that was the example I showed in the previous slides. The weird states enter a self-looping stage. We also have detour. The weird machine somehow finds its way back to the same state. And we have tunnel, where the weird states was never being generated, but the same state transitions was did not under the programmer's intent. And we wanted to say in this paper is that the weird machine does exist, and we're able to present it in actual graphs. So how did we go and conclude all of that? So now I present to you Fault Detective, a root cause analysis with include hardware redundancy plus scan chain. So now you have a core here. With this core, you have processor, peripherals, memory, and registers. It's completely fine by running it by itself. And then what I do is I duplicate this core multiple times. And every single core, they're able to run lockstep execution. So meaning that at the same clock cycle, they're able to run the same thing and the same exact program. What we did is that on top of that, we use a minimal hardware. We don't want it to overcomplicate things, so we use minimal hardware to connect them just to make sure that they can talk to each other. And then we do the fault checking in the software by redundancy. For example, 1 or 2 of this core here is faulted, and when they're running, they're able to talk to each other and then do the fault checking in the software. And once the core itself realizes that there's something is different, then what they do is they will detect the fault. And then all the cores will stop. And on top of that, we implement a scan chain. Therefore, we're able to provide high visibility on all the register bits to analyze which core is faulty, which core did something wrong than other cores. That's why we call this hardware redundancy plus scan chain design. And this is just the first step of Fault Detective. How to use this, it's in the next slide. So here, we have a time in the horizontal and then a software and hardware in the vertical. So once a fault is being injected in the hardware, we call this, so any registers that instantly get impacted from the fault, we call the fault root cause registers, which are the initial fault happened. And all these registers will impact continuously to the program. So now we have fault propagation until the fault is detected by the software redundancy. Again, we have hardware redundancy, and all of the cores will detect themselves. They'll be able to detect the difference among the core. And the reason we take a benefit of this, and it's very important, is that by having software redundancy detection, we're able to detect the earliest fault. So think about it. If you are doing a fault injection and by the time that you realize that your core is already faulted or your output is not giving you any information, you do a human reaction of the fault detection. At that point of time, it's already too late to do the fault root cause analysis because 90% of the bits in your core is already impacted by the fault. So the golden time to do the fault root cause analysis is within the fault being injected until the fault detected by the redundancy. So that's the golden time that you could emphasize the fault root cause analysis. And how do we get data, or how do we keep track of this period of time, is that we will be able to use the scan chain. So by using scan chain, we're able to document all the register bits. And therefore, we're able to document right before or right after the fault is being injected until the fault is being detected by the earliest reaction. And then by having all these register state, we're able to put on a story of what happened, how this fault being impacted from the initial fault, and track the fault propagation all the way. And so this is how, by using the scan states, we're able to plot the dynamic state transition graph for the sane and the weird machine. And also, this can also be applied on simulation and measurement. Okay, so in our paper, we did a simulation experiment on this, and we used layout data to do fault root cause analysis. So we actually tape out a chip. So we had a realization in ASIC. We use 6-core MSP for 30. There's no reason that we choose 6. It's just right under our budget. And we wanted to implement the real-world fault injection using layout data. In our paper, we did laser and clock, but there's no restrictions of any other type of faults. And what we wanted to achieve is that we wanted to make no assumptions of where the fault happened. That's why we will use the layout data. And let me walk you through this. So this is the layout distribution of our 6-core MSP for 30. You see each core has 4 banks of RAM, and then all of these cores are highlighted in the layout. And the gray bubble, these represents the standard cells. And you can see we have a scan chain that connects all of them. And what we did for the laser is that we will randomly select a region, And for this region, you need to select a size. Basically, we're mimicking the laser spot size. And whatever the laser hit, how many registers will consider those registers as faulty in the test bench. Same thing, this is the actual place and route for our chip. All these rectangular purple area, these are register bits, standard cells. And again, whenever these selected region hit, we will consider all the registers within the selected region as faulty. And that's how we implement the layout aware fault analysis in our simulation. So at the end, I wanted to demonstrate you an example based on the simulation what we did. So we did this with the verify pin 5 example. And these are the inputs. So you can see on purposely, I have made one input faulty. Therefore, it will never bypass the pin verification process. And these are the ADSTG and MDSTG graph of the same machine behavior of this implementation. Again, all these A nodes, these represents architecture saying states, which represents all the programmer visible bits. And we have microarchitecture saying states that represents all the bits in the design. And we have transition time. This is just the implementation. I wanted to recap on this. So we have verify pin 5, and then we have a trial counter test at the beginning, and then there are 2 bi-array compare, and then once you pass that, you return true. But in this case, because I set the inputs wrong, so it will always return Boolean false. And the purpose of this to demonstrate root cause is that I wanted to use one single fault to bypass the pin verification to make it return Boolean true. Okay, so I use this as for clock glitching. I glitched at clock cycle 173, and let's see what the graph tells us. Okay, so now we see that definitely, because I know that all these black highlighted area in the graph, these are the same machine where it will never take any other paths than the Boolean false. But now you see that new states are generated and just continue until clock cycle 200. Therefore, I know, okay, the countermeasure has been compromised. And then let's see what the root cause is. So a very small table here, this shows the fault root cause, which are the registers that got instant impact right after the clock glitch happened at clock cycle 173. And most importantly, I wanted to find out what's the reason that I broke the countermeasure. And there's only one reason that you could explain at the microarchitecture level is this E state here. So this is an instruction sequencer, and by having this bit toggled to D caused the instruction sequencer to skip 2 instructions. So what are the 2 instructions being skipped in this case? So let's see the assembly code. So I have showed the assembly code at the beginning of the verify pin 5. And this instruction here is right after this instruction, I inject my glitch. So F0E2 was never being executed. It just terminated. And then it will skip 2 instructions, and then we'll resume. So this instructions was being skipped. But this is fine, because what this does is it terminates the trial counter test. It doesn't do anything to the countermeasure. But what skipped next caused the trouble. So this is the next instruction that got skipped. What this does is that it will clear register R12, but R12 is used beforehand for the trial counter test. Therefore, in this case, here return Boolean false was never, the Boolean false was never being cleared and returned a 0 value. Instead, it will return whatever the value that's stored in this. And because of hardened Boolean is not implemented in this, therefore any positive value could compromise this countermeasure. And then that's how the countermeasure breaks. And at the end, I wanted to wrap up to say that fault detective can achieve real-time fault detection in the earliest possible moment by using hardware redundancy. And we can also identify the earliest fault by using a scan chain and track the fault propagation through a scan chain. Also monitor the behavior of the sane and the weird machine using graphs. And this can help to analysis how the application fails. And it will bridge the gap between the simulation and the measurement experiment. Thank you so much.
Thank you very much. So any questions? Yes, please.
Yeah, thank you for the talk. It was very interesting. Yes, if we...
Go back.
Sorry.
Do you want me to go back?
No, no, no. It's,
Okay.
so yes, if we consider, so in your example, you consider a very simple microarchitecture. So the MSP 4030 is quite simple. In practice, it may be that for one simple fault model, architectural fault model, there may be several microarchitectural fault effects that induce the same fault model at the architectural state. For example, the instruction skip could be induced by many fault effects in the microarchitecture. Could you distinguish between all those effects in the microarchitecture with your approach?
Could you elaborate your question again?
Okay.
Sorry.
Let's say, considering the instruction skip at the architectural level, can you distinguish between the many causes that lead to an instruction skip, but causes in the microarchitecture?
I see. So I think the most important thing of this presentation is that we are able to, I think it's this graph here, that we're able to track what happened within this period of time. And it's independent of what kind of fault that it's on that.
Okay.
So as long as you have access to, access to all this, you'll be able to find out why, and you'll be able to track out what happened for the root cause. Yeah. So I don't think it's attack dependent, because it's more like a technique that you can use to identify the root cause. No, this doesn't mean that you have one root cause. It can be multiple root causes. For example, you can see, so for example, for laser, you know what registers, and you know that, okay, you hit 3 registers. So you know that these 3 registers are your root cause registers. But for clock glitch, we don't know how many registers, and it can be more than 1 registers being root cause. Did that answer your question?
Yeah, probably, yes. We can discuss offline. Thank you.
No problem, yeah.
Okay. Oh, yes.
Yeah, thank you for the great talk. I'm curious about the implementation, actually. Like, kind of how much effort is it to kind of produce the structure with the multiple lockstep cores, implement the software, kind of fault checking? Like, is it something that you think would be simple to port to other systems, or is that a big lift?
So you mean the ASIC that we
Yeah.
did? Okay, so it's very simple. What we did is that we connect all the GPIO ports together of all the cores, and that's the only hardware we did. And then we implement a global stop to stop all the cores once the fault is detected, but we do everything in the software.
Gotcha.
Yeah.
Cool. Thank you.
Thank you.
Okay. Any other questions, comments? Yes.
Does it work? Yes, okay. Thank you for the talk. It was really detailed. I wanted to know about the implementation also, about the performances, because like implementing scan chains at the scale of a design had a lot of delays.
Yeah.
And did you like conduct some performance evaluation or?
No, we just simply used the synthesize to inject the scan chain, and it was no problem for us because like he said, MSP 430 is a very simple core. Yeah. Yeah.
Okay, yeah, that's interesting because yeah, I guess this tool can be really useful to be like run in an automated way to discover new root causes. But if it's slowed down a lot, then the capabilities of finding new root cause can be way less. So
I would say for simulation, it's no problem because you already have all the access to your design. You can document all the registers. For measurement, it might be trouble because I know for scan chain, every scan that takes time, but there's other ways that you can access your registers, like shadow registers. It doesn't have to be a scan chain, but we wanted to present this to let you know that there is actually a way that we can access and then combine the hardware redundancy with scan chain to perform the root cause analysis.
Okay, makes sense. Thank you.
you.
Okay. Any other comments and questions? So let's thank the speaker again. Okay, so it's time for close. Enjoy the banquet.